Welcome to this comprehensive one-shot session on physical chemistry for classes 11 and 12. In this video, we'll journey through the core concepts, key formulas, and essential problem-solving strategies that will help you master this subject. Whether you're preparing for your board exams or competitive tests, this session is designed to give you a clear, concise, and logical overview. Let's start by understanding what physical chemistry is all about and how it bridges the gap between physics and chemistry, focusing on the principles that govern chemical systems and reactions. Physical chemistry begins with the study of the states of matter, solids, liquids, and gases. Each state has unique properties, and understanding these is crucial for grasping further topics. We'll discuss the characteristics of each state, intermolecular forces, and how temperature and pressure influence matter. This foundation will help you as we move into more complex concepts like gas laws and phase transition. Let's explore how molecules behave differently in each state and why these differences matter in chemical reactions. Now let's dive into the ideal gas law, a fundamental equation in physical chemistry. The law combines several simple gas laws into one equation, PV equals nRT. Here P stands for pressure, V for volume, N for moles, R is the gas constant, and T is temperature. This law helps us predict the behavior of gases under different conditions. We'll also touch on the assumptions behind the ideal gas model and when real gases deviate from this behavior. Understanding this law is essential for solving many numerical problems. While the ideal gas law is useful, real gases often deviate from ideal behavior, especially at high pressures and low temperatures. This is where the van der Waals equation comes in, correcting for intermolecular attractions and the volume occupied by gas molecules. We'll discuss the significance of these corrections and how to apply the van der Waals equation to real-world problems. Recognizing when to use the ideal versus real gas equations is a key skill in physical chemistry. Thermodynamics is the study of energy changes in chemical systems. We'll start with the basic concepts: systems, surroundings, and types of systems, open, closed, isolated. Understanding these terms is crucial for analyzing energy flow during chemical reactions. We'll also introduce the laws of thermodynamics, which form the backbone of this topic. These principles help us predict whether a reaction will occur spontaneously and how much energy is involved. First law of thermodynamics, also known as the law of conservation of energy, states that energy cannot be created or destroyed, only transformed. In chemical reactions, this means the total energy of the system and surroundings remains constant. We'll discuss internal energy, heat, and work, and how to calculate changes in internal energy using the formula delta U equals Q plus W. This law is fundamental to understanding how energy is transferred during chemical processes. Enthalpy, represented by H, is a key concept in thermodynamics. It measures the total heat content of a system at constant pressure. We'll explore how enthalpy changes during chemical reactions, especially in exothermic and endothermic processes. Understanding enthalpy helps us calculate the heat absorbed or released and is essential for solving calorimetry problems. We'll also look at standard enthalpy changes and their significance in predicting reaction outcome. Second law of thermodynamics introduces the concept of entropy, a measure of disorder in a system. This law states that the total entropy of an isolated system always increases over time. We'll discuss how this principle explains the direction of spontaneous processes and why some reactions occur naturally while others do not. Entropy is a crucial factor in determining the feasibility of chemical reactions and understanding the flow of energy. Gibbs free energy, denoted as G, combines enthalpy and entropy to predict the spontaneity of chemical reactions. The formula delta G equals delta T. Deltas helps us determine whether a reaction will proceed on its own. If delta G is negative, the reaction is spontaneous. If positive, it is non-spontaneous. We'll see how to apply this concept to real problems and why it's so important in both chemistry and biology. Chemical equilibrium occurs when the rates of the forward and reverse reactions are equal, resulting in constant concentrations of reactants and products. We'll discuss the dynamic nature of equilibrium, the equilibrium constant K, and how to write equilibrium expressions. Understanding equilibrium is vital for predicting the outcome of reactions and for solving related numerical problems. Chatelier's principle helps us predict how a system at equilibrium responds to changes in concentration, temperature, or pressure. When a change is applied, the system shifts to counteract that change and restore equilibrium. We'll look at practical examples such as how increasing temperature or adding more reactant affects the position of equilibrium. This principle is essential for understanding industrial chemical processes. Ionic equilibrium deals with the behavior of ions in solution, especially in weak acids and bases. We'll discuss the concepts of dissociation, ionization, and the calculation of pH. Understanding ionic equilibrium is crucial for topics like buffer solutions, solubility product, and titrations. We'll also look at how to use the Henderson-Hasselbalch equation for buffer calculations. Acids and bases are central to many chemical reactions. We'll define them using the Arrhenius, Bronsted-Lowry, and Lewis concepts. The pH scale measures the acidity or basicity of a solution, and we'll see how to calculate pH for strong and weak acids and bases. This section also covers the importance of pOH and the relationship between pH and pOH in aqueous solutions. Buffer solutions resist changes in pH when small amounts of acid or base are added. We'll discuss how buffers are made, their importance in biological and industrial systems, and how to calculate their pH using the Henderson-Hasselbalch equation. Buffers play a vital role in maintaining the stability of chemical and biological systems. Solubility product, or KSB, is a constant that describes the equilibrium between a solid and its ions in solution. We'll learn how to write KSB expressions and calculate the solubility of sparingly soluble salts. This concept is important for predicting precipitation reactions and understanding the limits of solubility in different conditions. Colligative properties depend on the number of solute particles in a solution, not their identity. These include boiling point elevation, freezing point depression, vapor pressure lowering, and osmotic pressure. We'll discuss each property, their formulas, and how to solve related numerical problems. Colligative properties are widely used in real-life applications, from antifreeze in cars to medical solutions. Raoult's law explains how the vapor pressure of a solution is related to the mole fraction of its components. This law is key to understanding colligative properties and the behavior of solutions. We'll look at the mathematical expression of Raoult's law and see how it applies to ideal and non-ideal solutions. This knowledge is essential for solving problems involving vapor pressure and solution composition. Electrochemistry studies the relationship between electricity and chemical reactions. We'll introduce the basic concepts of redox reactions, electrodes, and electrochemical cells. Understanding how chemical energy is converted to electrical energy and vice versa is crucial for topics like batteries, fuel cells, and corrosion. Redox reactions involve the transfer of electrons between species. We'll define oxidation and reduction, identify oxidizing and reducing agents, and balance redox equations using the ion-electron method. Mastering redox reactions is essential for understanding electrochemical cells and many biological processes. Electrochemical cells convert chemical energy into electrical energy. We'll discuss the construction and working of galvanic, voltaic, and electrolytic cells, including the role of electrodes and the flow of electrons. Understanding cell notation and the difference between anode and cathode is key for solving electrochemistry problems. Standard electrode potential measures the tendency of a half cell to gain or lose electrons under standard conditions. We'll see how to use standard reduction potentials to predict the direction of redox reactions and calculate cell potentials. This concept is fundamental for understanding how batteries and electrochemical cells work. The Nernst equation allows us to calculate the cell potential under non-standard conditions. We'll break down the equation, explain each term, and show how to apply it to real problems. This equation is vital for understanding how concentration affects the voltage of electrochemical cells. Electrolysis uses electrical energy to drive non-spontaneous chemical reactions. We'll discuss the process, its applications like electroplating and extraction of metals, and how to calculate the amount of substance produced using Faraday's laws. Electrolysis is widely used in industry and is a key topic in physical chemistry. Faraday's laws quantify the relationship between the amount of substance produced at an electrode and the quantity of electricity passed through the electrolyte. We'll explain both laws, their mathematical expressions, and how to use them in calculations. These laws are essential for understanding the quantitative aspects of electrolysis. Chemical kinetics studies the speed or rate of chemical reactions. We'll introduce the basic concepts including reaction rate, rate law, and factors affecting reaction rates. Understanding kinetics helps us control reactions in industrial and laboratory settings, making it a vital part of physical chemistry. The rate of a reaction measures how quickly reactants are converted to products. We'll discuss how to express reaction rate, the units involved, and how to determine the rate from experimental data. Understanding the rate is crucial for optimizing chemical processes and ensuring safety in industrial applications. Order of reaction refers to the power to which the concentration of a reactant is raised in the rate law. Molecularity is the number of molecules involved in an elementary step. We'll clarify the difference between these terms, how to determine reaction order experimentally, and why molecularity is always a whole number. Integrated rate laws relate the concentration of reactants to time for different reaction orders. We'll derive and apply the equations for zero, first, and second order reactions. These laws help us analyze experimental data and predict how concentrations change over time. The half-life of a reaction is the time required for half the reactant to be consumed. We'll discuss how to calculate half-life for different orders of reactions and its significance in chemical kinetics. Understanding half-life is particularly important for radioactive decay and pharmacokinetics. Several factors influence the rate of chemical reactions, including concentration, temperature, catalyst, and surface area. We'll explore how each factor affects the rate and why understanding these is crucial for controlling reactions in both laboratory and industrial settings. The Arrhenius equation relates the rate constant of a reaction to temperature and activation energy. We'll break down the equation, explain each term, and show how to use it to calculate activation energy from experimental data. This equation is fundamental for understanding how temperature affects reaction rates. Collision theory explains how chemical reactions occur and why reaction rates differ. It states that molecules must collide with sufficient energy and proper orientation to react. We'll discuss the key ideas of collision theory and how it supports the concepts of activation energy and reaction rate. Catalysts speed up chemical reactions without being consumed. We'll discuss how catalysts work, the difference between homogeneous and heterogeneous catalysis, and their importance in industry. Catalysts are essential for efficient chemical manufacturing and environmental protection. Surface chemistry studies phenomena that occur at the interface of two phases, such as adsorption, catalysis, and colloids. we'll introduce the basic concepts and their significance in everyday life and industry. Surface chemistry is crucial for understanding detergents, catalysts, and even biological membranes. Adsorption is the accumulation of molecules on the surface of a solid or liquid. We'll discuss the difference between adsorption and absorption, types of adsorption, physical and chemical, and the factors affecting adsorption. This concept is widely used in water purification, gas masks, and catalysis. Colloids are mixtures where one substance is dispersed in another at the microscopic level. We'll explain the properties of colloids, types, sols, gels, emulsions, and their importance in food, medicine, and industry. Emulsions like milk are a special type of colloid with practical significance. The Tyndall effect is the scattering of light by colloidal particles, making the path of light visible. We'll discuss how this effect helps distinguish colloids from true solutions and its applications in science and daily life, such as the blue color of the sky. Surface chemistry plays a key role in catalysis, especially heterogeneous catalysis where the catalyst is in a different phase than the reactants. We'll explore examples like the Haber process and catalytic converters, highlighting the importance of surface area and adsorption in these reactions. Colloids exhibit unique properties like Brownian movement, electrophoresis, and coagulation. We'll discuss each property, their significance, and how they are used in practical applications from medicine to environmental science. Surface chemistry has numerous applications in daily life and industry. From detergents and soaps to catalysts and sensors, understanding surface phenomena helps us design better products and processes. We'll highlight some key applications and their impact on technology and the environment. Thermochemistry focuses on the heat changes that accompany chemical reactions. We'll discuss enthalpy changes, calorimetry, and Hess's law, which allows us to calculate enthalpy changes for complex reactions. Thermochemistry is essential for understanding energy flow in chemical processes. Hess's law states that the total enthalpy change for a reaction is the same, no matter how many steps the reaction takes. We'll see how to use Hess's law to calculate enthalpy changes for reactions that are difficult to measure directly. This principle is a powerful tool in thermochemistry. Calorimetry is the measurement of heat changes in chemical reactions. We'll discuss the types of calorimeters, how to perform calorimetric calculations, and the importance of specific heat capacity. Calorimetry is widely used in laboratories to determine enthalpy changes and study reaction energetics. Physical chemistry isn't just theoretical, it has real-world applications everywhere. From the batteries in your phone to the food you eat and the medicines you take, the principles we've discussed play a role. Understanding these concepts helps you appreciate the science behind everyday phenomena and prepares you for advanced studies. Let's wrap up our one-shot journey through physical chemistry. We've covered states of matter, thermodynamics, equilibrium, electrochemistry, kinetics, and surface chemistry. Remember to focus on understanding concepts, practicing numerical problems, and connecting theory to real-life examples. With consistent effort and a logical approach, you'll be well prepared for your exams and beyond.